Welcome to Talkin Science, where we dive into the latest news from space and science. Dr. Judith Klatt is here to discuss a very interesting theory she's helped to postulate. Dr. Klatt, thanks for your time.
You're welcome.
This is Trekzone's Talkin Science. And you can get exclusive behind-the-scenes info and first-play access to all Trekzone podcasts by becoming a member today. Click join on every Trekzone video on YouTube. Go to the trek.zone/support or scan the QR code on screen throughout the show. Now, it's back to you, Matt.
Well, thanks very much, Ross. Dr. Klatt, you and an international team have theorized that the rise of oxygen levels on early Earth are related to the length of the day, specifically the slowing of our young planet's rotation as the gravitational forces of the moon came into play. Can you elaborate on this fascinating theory, please?
All right, maybe to start with a big question that Earth scientists are struggling with for many years already. It's about how actually oxygen came to us, right, and allowed higher life, such as us, to flourish at some point. And there are a million questions around the rise of oxygen. What we know definitely is that it was invented by bacteria, by cyanobacteria, before the great oxidation event about 2.4 billion years ago. We also know that after this event, actually oxygen levels still relatively low for 1 to 2 billion years, the so-called boring billion of oxygen. And then there was another major rise in oxygen, and slowly we're getting towards modern levels, right? And dinosaurs, for instance. Before reaching these modern levels, actually the world was primarily microbial, right? So there were no higher life forms as we know them today, but actually bacteria and other microbes were dominating the Earth. So one of the big questions is how these microbes might have interacted with Earth's oxygen. And how they might have affected this pattern. This is what I usually deal with, but at some point, a physical oceanographer approached me and asked me, could day length have had an effect on this? And I was like, no, definitely not, because it shouldn't affect how much oxygen, for instance, is produced by cyanobacteria. But after thinking for about a year, I realized it should matter in so-called microbial mats, another really common form of life on Earth for most of its history again. So we can imagine this as structured microbial communities. We nowadays still find them and don't find them pretty usually in extreme environments, but they were really important on an ancient Earth. So the thought was, how could day length have mattered for these systems and for their oxygen release into the atmosphere? And then we realized, well, there might be actually a link between day length and oxygen release, which is based on the physics of diffusion in these mats. And then we looked at the pattern of Earth's oxygenation and the pattern of Earth's rotation rate, and they were stunningly similar. So I was talking about this boring billion, and some models for Earth rotation rate actually suggest that during this boring billion, also day length was constant. Right, so that we actually end up with patterns that are stunningly similar. So we kept thinking about this, how oxygen release and rotation rate might have interacted. We built a model with my colleague Arjun Chenu, and simulated basically dial cycles in silico. Found out, there is a mechanistic link, indeed. Then we went a big step and did some upscaling, let's say, from dial scales to geological time scales, and tried to find out if this small mechanistic effect, like dial microbial effect, could have mattered on a global scale. And with a lot of assumptions in it, it could have indeed mattered. And the outcome of this is that maybe rotational rate, so day length, could have indeed in fact affected the oxygenation of Earth, besides many other factors, though. It's still a hypothesis, right?
Exactly right. It is absolutely fascinating, and a place that is very critical to some of this research, that you found some similarities to early Earth, is Lake Huron. That's sparked the team's imagination. What is it about the conditions there at Lake Huron that are comparable to early Earth?
Right. So I've mentioned before these microbial mats, right, that might have been all over the place on like covering all the coasts of Earth for a very long time in its history. So we nowadays only find them in these really weird environments, extreme environments, as we would call them today, like hypersaline or lots of UV radiation, a lot of sulfur, and low oxygen, right? Because this is what Earth was like. And this is actually the case in this Middle Island sinkhole in Lake Huron. There is low oxygen groundwater that seeps out underneath the water column of Lake Huron in a kind of underwater waterfall fashion. And then it stays underneath the water column of Lake Huron and excludes higher life such as fishes and so on. They don't want to go in there. And this allows them microbial life to flourish. And we have these beautiful microbial cyanobacterial mats there. Right. And well, it's because of the low oxygen and because no bigger life forms are there. It's like a window into the ancient Earth, let's say. Of course, we wanted, like we had this beautiful model where we saw that there is a relationship between day length and oxygen release based on physics. And now we really wanted to go for a bit more biology. And we took mat samples from this sinkhole and exposed it to a simulated dial light cycles of different lengths. And then we checked what's the oxygen export from these mats. And in fact, it was strongly affected by day length, right? In this really complex, weird microbial mat, the dependency was steeper than in most of our models, actually, even.
It's an incredible thought to consider that oxygen production was never the intent of these microbes at the early stages of Earth. Microbes, algae, plants, they really just wanted to capture some energy from sunlight to survive, the byproduct of which is oxygen. And with a couple of helpful pushes along the way, they've created an oxygen rich atmosphere that we basically owe our existence to. It's incredible to think that, really, isn't it?
It is. I mean, it's the biggest invention, let's say, this onset of oxygenic photosynthesis, which was really just because maybe there was not enough sulfur around at that point, right? So Earth was based on iron and sulfur cycling, and there was methane in the atmosphere. It was really harsh and weird. And in some local spots, there might have just not been enough of that. And then at some point, cyanobacteria evolved and could use water, light, and CO2 and make this amazing process happen that really changed the face of our planet.
What was the motivating factor for you to hypothesize that increased daylight leads to increased oxygenation?
Well, in general, I'm obsessed with studying microbial mats and how they might have impacted actually this pattern of Earth's oxygenation. I usually look at things like redox conditions in the water column, like how much sulfur is there, how much light is there. And then there was this really nice chat with Brian Arabic, a professor for physical oceanography, who really just raised this question: could there be a relation to Earth rotation rate and day length? So that really triggered some thoughts. It might not have been a new discovery that there are similarities in the patterns, but that there might actually be a mechanistic link was then really mind-blowing, let's say.
And one thing that I love in science and learning about science here on Talkin Science is that this international community of scientists get together every now and then, listen to some lectures, listen to other people speaking, read some theories and some hypotheses, and
Right.
the work of others as well, and discover similarities and ways that your research might help someone else. And in fact, that's sort of where this whole thing sort of got started. You're thinking there was helping another research project from members of the team. Just incredible to think that this was sort of just off to the side, but became a pretty important theory as well.
Yeah, I mean, this whole project in itself was super exciting because of the interdisciplinarity. I mean, we're working with micro or even smaller molecular diffusion scales. Then we move to global budgets and all that under the consideration of the Earth-Moon system, right? So this was super fun, I have to say. And yes, it was because of communication between scientists that this could happen at all, right? When different disciplines come together and just have a chat. So I really like also how this story developed overall. And I'm super curious how it's going to be perceived by the scientific community and what it's going to trigger.
What's next for this theory? How are there ways that we can prove it, or what's sort of the next steps in its journey?
I mean, there will be a lot of validation steps. For now, it's an idea, right? We have a mechanistic link that's based on simple physics of diffusion and mass. But now we really have to understand more about how it could have mattered, right, on a larger scale. And we had to make a lot of assumptions that now need to be validated more and more. It's like, how does this link to signatures and the geological record and so on? So there's a lot to be done. For now, it's an idea. But let's see what's going to happen. So I'm particularly curious, of course, more studying more cyanobacterial mass and trying to find these signatures that I then can communicate with geologists.
Well, it is absolutely fascinating research, an incredible idea, Dr. Klatt. Thanks for beaming into Trekzone today. I really appreciate it.
Thank you for inviting me.